to do some other stuff, like actually draw the full line. Right now it's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines of code, and it loops just like the last 5 over and over and over again to keep drawing points. This is the clock speed I'm currently running at to make sure it's like stable enough. It's 4, 8 plus another 4 is 12. Plus another one is 13, so you double that, that's 26. So the duty cycle is 50% at 20 ticks, or 26 ticks. So it means it's an on pulse for 13 ticks and an off pulse for 13 ticks that comes in through here. So this thing seems to be picky on its pulse length that it gets. So it actually gets, this is a 4, 8, 12. So this plus this, that's a 13. So this here matches this frequency here. And this is just to make sure our pulses get the right length. That's all this is really for. And then this is our program counter. This outputs what line of code to be reading from. Right now it's saying line 6. This is our input to the program counter so we could give it branches. So the instruction decoder is basically all right here, right in front. And this is the actual decoder for the instruction decoder. And so what I'm going to do is I'm going to change the inputs instead of being a slope of 2 and an intercept of 1. But I cleared the screen accidentally when it plotted the first point. So it would have plotted a point here, but I cleared the screen while it was plotting that. So I'm going to give it some other values, and we're going to run it, and as it's running I'm going to show other parts of the CPU. So the way we change the values is this first line of code here is the slope, and this line here is the intercept. So over here we have one, 2, 3, 4, 5, 6. So when we're loading in immediate, that's what this line here says, load immediate, load slope. So the load immediate line means we have 6 bits for an immediate. So we could load in a value of 6 bits large, but the screen is only 4 bits by 4 bits large. It's 16 by 16. So that would be dumb to load in a 6-bit value that you wouldn't see on the screen. So here we're just plugging in the value 2. That's how we got a slope of 2. But let's change it to, say, a slope of 3. Oops, goes here. And then instead of an intercept of 1, let's do an intercept of 2. So now we'll run that. All I have to do is come over here, click the thing that says enable branch, and then clock this a few times. We'll see that that comes in, and then this goes to 0. So this will retain at 0. Okay, so now that the CPU is at line 0, we're going to come up here, and we're going to click clear screen, and now the screen's going to go away. And now we come over here and remove this, which is telling it to branch line 0, and now it's going to be allowed to increment through the lines of code here. So you'll see the outputs, it'll say 1, and then, or it's 3 and then 2, because there's a slope of 3 and then an intercept of 2, and this is just coming right out of the ALU. So it's not like a particular output, it's just coming right out of the ALU, and then when it gets to, yeah, it branched already, or when it gets to line 5, it plots. So we have an intercept of 2. So there's our intercept of 2. And then when it gets to the end here, it comes back to this line right here, which tells it to plot a new point. So every time it branches to this line, this is the plot a point line, and the rest is logic telling it how to calculate the slope. And the last two branches, or last 2 lines are branch. So it takes 2 lines to branch, one for compare and one to branch actually. So here's the line that we get drawn so far. And it's going to branch one more time. And then I'm going to kill the clock. And there should be another point up here, but maybe not. Okay. Yep. So we have a line drawn on our screen. And the way this works is quite simple. We have we let some registers equal some stuff. So our register 1 is going to be the slope, register 2 is going to be the intercept. So the slope and the intercept are what we define. So when we edited those over there, that's register 1 got the slope and register 2 got the intercept. As the code started going through, we let register 3 be the x register, the one that would be being sent to the screen and being like, this is the x value. So we want to initialize that to 0 and then increment by 1 every time. But register 4 is the y-axis. So we want to initialize that with the intercept that the user gives it. And then over time, we just add the y value, or we add the intercept to the slope value in R1. So we basically add R4. We have an equation R4 equals R4 plus R1 over time, and that's how we keep calculating where the next point goes. Because each time we increment over by x, we increment x over by 1, and then oh, you can ignore this. And then so I was writing some code to actually that would then draw the lines instead of just plotting the points of a line. And all you would do for that is you'd use some extra registers and you'd have some comparisons, and you'd have a counter. And basically, you wouldn't increment x every time, you'd increment y every time until the y is equal to the slope. And then once y is, or some register is equal to the slope, and once that register is equal to the slope, then you increment x, you reset that register to 0, and then you continue, and then every time you plot, you increment that register until it's equal to the slope, and then that tells you when to increment x. So that'll tell you how to be like, okay, we're here, but 1 isn't equal to 3, so we're going to increment again. And okay, 2 isn't equal to 3, so we're going to increment again. Okay, 3 is equal to 3, so after we plot, increment x. Okay, then plots, then does the same thing, and that's how you get to fill in the lines. But I'm just showing you guys how this works for now. So the heart of this thing here is an ALU. Now this ALU isn't the best designed. It was grabbed from the school server on OR. This is actually built on the school server on OR for a demonstration for somebody else that wanted to learn how CPU is built, so I built one for them. So this ALU is not anything fast or compact, and then it comes into a shifter. The shifter is right here. Pretty nice compact shift register. It's not even a register, it's just a shifter. It shifts values down. That I built onto the ALU. That I didn't build this ALU myself. It's a CCA ALU, and I don't really mess with CCA logic. So then I have registers on both sides. Whoops, come on. Registers on both sides, and the outputs of the registers bus into the inputs of the ALU, like that. And the same on this side, so it's symmetric. And then this is saying invert A, and this is saying invert B. So if you toggle the lines, it'll invert the outputs. And then it goes into the ALU for math and whatnot. And then the way we control the screen is kind of easy. So the bottom 4 bits of the register reads before they get branched and brought back into the input of the ALU. This is why I like simulated dual read ALUs, or data loops, I guess I should say, is because then this line gets branched up to here. We have registers here. And so there's a command for my screen operation called screen, and there's parameters in that, and in those parameters I have like clear screen, plot points, or load registers, load XY registers. So load XY register means whatever value you read from it, like let's say you put 5 in the blue here, the value 5 would come over into here, decode the value 5, decode the 5th register from here, so it would be the 1, 2, 3, 4, 5. It would read the value out of this register. It would take the lowest 4 bits of that value, send them up to here, and then read or save those 4 bits into this register. What that accomplishes is storing a value to be decoded by the screen. So let's say we had the value 1 here in our x, or in our, sorry, this is the y side. If we had the value 1 here in our y, it means we'd be working on the row of bits, or row of pixels, one line up. Then on the x-axis, a similar thing happens, and then that narrows it down which x-axis, which one of the pixels on that particular y-axis do we want. And so here's the value 5 coming out. Value 5 would come up, would get saved into the register here, and currently we have the value 4. So this tells it, oh, okay, over here is the value 4, and so I don't want to actually write the point right now, but the way I could prove to you that it's the value 4 is if we come over to the right pixel. So this is 0, 0, 1, 0, and so this decoder is actually off, where if I were to remove this like this, these decoders are on. So you can see how these decoders are on, but that one's off, and the rest are on. So that means this is the position it's decoding to. You can see how that's off right there. And so since this is the position it's decoding to, the moment that this line comes on and turns this on, it allows it to write. And so this is basically the command that says plot the pixel. And so we plot the pixel when we choose to. So we have the decoder already decoding the value, and then we just open up the decoder at once to plot. And so that's the way the plot works. Yeah, and then I guess I'll show the instruction set because it's really basic. So the way the instruction set works is if you enter zeros on the yellow, then the computer is not going to do anything. It's called a no operation. If you enter a 1, so 0, 0, 0, 1, you're going to add. 2 is add with carry, 3 is subtract. Then we can NOR and XNOR. Then we can downshift. We can access RAM, which I haven't hooked up or actually implemented on this thing yet, because there's no really real point. I don't need that much memory. It would just be more for the show. It wouldn't really be used much. So then I have the input scheme, which I actually haven't hooked up yet either, because I'm just using the load immediate to get my values in. I just hard code them for now. The screen, well, obviously, yeah, we have a screen. So the way this works is it uses 4 bits from the A and B as the X and Y respectively. So here's the A and here's the B. I guess that's backwards. It should be the Y and X respectively. Can I edit that? No, I can't. How do I edit? Is there a way to edit? Nope. Okay. Well, it should be Y and X register respectively, because this one is the Y register and this one is the X register. So the way that works is you put in, let's say you wanted to load register 3 and register 5. So basically the way this works is the value in register 3 gets sent to the y-axis, and the value in register 5 gets sent to the x-axis. That's the way that screen operation works. There is no write, because you're not writing to a register in the ALU. The screen command knows to be writing these values to the screen registers over there, and on that side over there. And then the other thing which we can do with the screen is we can clear screen, we can load the X and the Y, and we can plot. I didn't split the X and Y individually, because the way this ALU is designed, it can load both at the same time because it has access to the left register bank and the Y register bank at the same time. Then we have our compare operation. So what that logically does is it subtracts A and B, and it saves the carry out and if 0 flags. It just looks at those flags and saves them. Then the branch operation says, go look at the flags, and then if the conditions that are set by the user is true, as in the conditions set match up with what the flags are, then allow the branch to happen. So the way this works is 0, 0 is branch if equal, 0, 1 is branch if greater than, 1, 0 is branch if less than, and 1, 1 is branch if shift underflow, which I haven't hooked up yet because I haven't felt the need yet, but it can be hooked up because the thing has underflow, but I haven't decided to do that yet. So anyway, the way this works is if you want to do a non-conditional branch, you still have to do the compare function, and what you do is you compare in the A register. Instead of putting in a register, you leave it blank, and in the B register, instead of putting in something, you just leave it blank. And so that's reading R0 with R0, and in a computer, the register 0 is called the 0 register. You can't write to register 0, and the output of register 0 is always 0. So what this is doing is it's comparing the value 0 to the value 0 over there. Well, 0 is always equal to 0, right? So since 0 is always equal to 0, I mean, I guess you could put in this register and this register because they should match. So the same register should always match the values. But just in case there is the chance that some registers got corrupted, you always, if you just use the 0 and 0, you know your branch is going to work every time when you're doing unconditional. So you compare 0 register to 0 register, and then you branch if they're equal on the next line. And that's basically how you do it, a unconditional jump. And then conditional jumps are just comparing and then actually checking for or comparing the registers that you actually care about. So is A greater than or less than B? Then you plug in the registers A and then B, and then on this you check the flags and branch if true, and if not, then it goes to the next line. And then of course there's a load immediate, and the way the load immediate instruction works is it's the value 13, 1, 1, 0, 1. The gray represents ones in this scheme, and the yellow represents zeros. So 1, 1, 0, 1, and it gives you a 6-bit immediate, like I said earlier. But we're really only using the first 4 bits, and really even less than that, because if we used like all 4 bits, then like let's say we put in a y-intercept of 11, then our points are starting here and they're going to run off the screen really quick. So because this is Minecraft and your screens can only be so big without being monstrous, yeah, I decided to narrow it down to a 6-bit immediate, really, because also there's 6 program lines, six bits for the program counter here. So that's all. Whoops, this isn't even hooked up here. Nice. Not that there's even 6 bits worth of code here. There's only 4 bits worth of decoders, and I only have like 10 lines hooked up right now. And I have various other codes that run like. So I had to edit the CPU because it wouldn't allow me to do, like, let's say I wanted to increment register 4, it wouldn't let me say register 4 equals register 4 plus 1. It would say, I would have to say register 5 equals register 4 plus 1, and then register 4 gets register 5. Anytime I wanted to increment, or anytime I wanted to do an operation like that that involves saving to the same register it was coming from, required me doing two lines like that. And so then I added one line right here, which comes down after some delay, and then allows my registers to write. So this is my write decoder. It's 3 bits, and then I added one extra bit that says when this turns off here, then actually allow whichever bit was decoded to be written to. And then so now I can control when my writing happens. It doesn't happen all the time when a line is being read. It only happens one time on a pulse that happens after some amount of delay. Because I've figured out the delay, I'm able to now say register 4 equals register 4 plus 1 without opening some sort of infinite loop that might accidentally add register 4 equals register 4 plus 1 twice before I stop allowing the register to read. You know, so you have to only open the register for a certain amount of time to let it read the value, but close it before the value comes back and updates itself. And so I was able to do that with the CPU, and I'm able to get it to draw lines, and of course there's plenty of other things that this will be able to do, but I will show you something cool coming up. Okay, so I'm on the build server of Ore, and I have this CPU here, and so I was thinking maybe I could do a tutorial about how to build basically this exact CPU with a screen and everything, be able to draw up lines. I'm going to implement the same instruction set, and I'll actually finish this tutorial this time. And what I'm going to do, instead of focusing on literally the nitty-gritty of each part, I'm going to give schematics for this, and then each time I build, I'm going to update the schematic and then post it. And so you guys can just start from where I am currently in whatever video you're watching, or you'll be able to start from scratch from the beginning with the few schematics I start from the beginning. Because here's the deal. This is the CCA ALU that I'm going to be using. Look at the size of this thing. It's maybe like, it's less than 15 blocks long. The CCA ALU in this one, slash speed, I guess I should disable chat. Okay, so I guess I can't type right now to do commands, but anyway, over here, the CCA ALU in this thing is massive. It's from the beginning here. Mine would end here-ish, and this one keeps going all the way to about here. And then these registers here are 3 wide, whereas the registers over on that we're going to be using are 2 wide. So I'm not going to do a demo on how to actually build the registers and build the CCA ALU, because these have gotten insanely compact, and I know how they work, but I don't feel like having to explain it. I'd rather just be able to use them as a black body, and then if you guys want, you can learn how these work on your own by examining the schematic, because it's basically really easy. Here's the data, and here's the read, and here's the clock. So this is the write line, and here's the read line, and then they alternate back and forth. But anyway, here's some really compact registers that we're going to be using, and the compact ALU. So I'm just messing around with a downshifter that we can stack at the end here to make this thing work really nicely instead of sticking it here. And then basically that'll be copied over here, and then we'd just be building on top of this. We'd be building that CPU that we see over there on this hardware, so it'd be much faster, much smaller, because that hardware was found on school and this hardware is found on build, so obviously the people on the build server are going to have much more superior hardware. So that's what's going to be coming in the future. I hope you guys are excited.